Okay, so this is my version of a this is my version of a comparator circuit. It's all of transistors, and this is kind of the schematic for the logic diagram of it, for some part of it. What this is about is I have two numbers here in binary, B register and A register, and these are the decimal outputs here. Right here, this is the A decimal output, and this is the B decimal output. We start here from 0 and go to 7 from left to right. So what I'm doing is I am using a comparator circuit here with some logic circuitry here for the output that will cause register A to match register B. So if register B should change, with the button over here, I'll hit this here. As I hit this, that should change register B. As register B changes, register A will change to match it, and then when it matches it, it stops. And so now if I were to go back with register B the other direction, register A will again go back to match it. So what that's doing is, if I were to, let's say, now what I'm going to do is I'm going to input on this switch here, and I'm going to cause register A to change. Let's say some sort of anomaly or something comes through and causes register A to change off of the set point here. So as I change that, it wants to keep on coming back to its original set point to match register B. So this would be what you would use for. Now this is the kind of function that you get with these analog or these comparator circuits that for voltage control and stuff like that. But this is my version of it in transistors and stuff like that. So anyway, it works. That's what's pretty cool about it. So what's pretty neat is that if I were to increase the frequency of the clock drive here, and I'll explain a little bit what's going on here later on, then I can, when I hit this button here to cause register A to change, it's going to come to a point where it's going to lock in position that it won't even change at all when I hit that button. So that'll be coming up next. Okay, now let me see if I can give a little bit of explanation here of what's really going on here first. These here AND gates right here is in the comparator circuit, and register A is feeding in to each one of these AND gates here, and register B is feeding into here. So we have two sets of 3-bit registers for A and B, and then we have the scan lines that come through. So what happens is, during a scan, it will scan each one of these AND gates, and what would happen is the AND gate that's on with the most significant bit will send its data out, and it will route it out to the control unit here, which would do all different kind of calculations in the output it needs to do. If it goes to the A greater than B route, then what that does is that will turn on a flip-flop that will turn on a switch, so that whenever the clock comes in, it switches it from a high value to a low value in numbers. If the A less than B comes on, then it routes it down to here, which is just a clock only, and leaves the switch down off. That's the logic diagram of it. What this is here, these are inputs from the counter, the program counter, or the instruction register, we can call it. Now that would be here. This is the instruction register here. This is 3 bits of toggle flip-flops with some steering circuitry here so they can count up and down. These are some time delay units to make these work properly. This here causes these three to talk to each other so that we can get a decimal output here from 0 to 7. And that's 8 bits of information. What it is, that is 8 instructions per cycle. I only need 5 of them. The first 3 here would be for scan lines. This next one is an input to the AND gates that would turn on the controller here, which is right here. Turns these AND gates on, which then does the clock, either with the switch down or the clock. That's just a clock frequency there. And then the last one is a reset, which causes all these flip-flops to go back to 0 again for the next scan line. So what happens is we have the flip-flops in register A and in register B are fed into the magnitude comparator here and hold that data there, which is being done right here. Now this is holding his data. So now when the scan lines come through, 0, 1, and 2, those scan lines are connected to the magnitude comparator circuit, and it scans from 4, 2, and 1, from the most significant bit to the least significant bit. Whichever one it finds on first that has the highest bit on, that's the one that will route into here. In this case here, if A was greater than B, like we said, that would route this direction here, and it requires a switch down signal to come in, and then for the counter input to turn both AND gates on, and only one will come on, depending on which one here is on, that routed to clock the A, which would clock it down, and then vice versa with this here. Now another thing that makes this work is that whichever output comes out here, if this flip-flop comes on here, it automatically locks this one out. It sends a signal to reset this and keep it held at reset so that it will not come on. So no matter what bit it finds during the scan below here, it will not register here because this is off, because this one's on. So they both cross-couple each other, both flip-flops, to keep each other off. So when one is on, the other one's off, back and forth. Now, the reset data comes in as the last instruction cycle to clear all three of these flip-flops. Now that's how this is able to determine which way to route the data that's coming into it, whether to route it to make this A register go to the left or to the right, depending on where this is at in relation to this, okay, A and B. Now, as we said, I have the clock frequency going slow here, and so you can see it's the 8 instructions are going through the cycle here. So if I were to change by changing the B value, the B register again, I'll clock up. The A register is clocking over until it reaches it and stops. And the same thing for the reverse of it. It follows it. Now again, if we go over to the button to change the A register only, it will always, when I let go of it, it will always go back to its original position, which is seeking the reference voltage, reference point. Now, like I said, what we're going to do now is I'm going to start speeding up the clock frequency so that these 8 instructions will start running faster, and this will start running closer to computer speed now, and that's coming up next. Okay, so now I have my audio generator hooked up here, and that's now clocking the instruction register. So now again, I'll just do a quick demonstration at this speed here again, how the A follows the B, and there's a little delay. Okay, so there's a little delay there. If I switch A only, you got some delay there. But now if I begin to switch the clock frequency a little bit faster now, so let's go ahead and take this times 10. So now we've got some faster motion going here. We've got quicker clock speed, therefore we have quicker instruction cycles now. So now let's see how quick the A register chases the B register now. Here we go. It's a lot quicker now. Now let's go ahead and again hit the A only. It's very difficult to knock it off balance. It comes back very quickly now. That's just at 10 times the clock speed. Let's go to 1,001 kilohertz. Okay, so now there is 1,000 clock cycles coming in. There's 8 instructions, so that's 125 times. This here goes through 8 instructions 125 times per cycle, or per second. So now we have this. Now here we go. Let's move the B. The A moves right with the B, right in line with it. If I try to knock A off now only, I am hitting the button as quick as I can, and it jumps back so quickly. I cannot get that to stay off the set value because of how many instruction cycles are working at one time, or at per second. So it's picking up every input of the B value. It's picking it up because it's going through 125. It's going through 8 instruction cycles 125 times per second. So anyway, that is my design of a 3-bit magnitude comparator circuit, and the function of it, using it to make a output signal follow a reference signal using digital digital instructions like a computer would work. And it works pretty good. I'm pretty happy how this came out. Let's go ahead and turn this back down again to there. And we'll play with this here a little bit this way again. See how slow that goes now? Because of the instruction cycles are going slower now. But it's pretty cool how that works. It's just so neat how that works like that. Yeah, but it works, and I just wanted to share how that works. Thank God that came out really good, works good, and so thank you for watching. Bye-bye.